is in Lévy-based hybrid models. Okay, and I hope there won't be typos in your slides.
Yeah, it's a great pleasure. I mean, George just left, but nevertheless, let me thank him for his efforts to bring us back to this wonderful institute. Now, this is a project which was done at the Freiburg Institute for Advanced Studies. The three of us were Thorsten Schmidt and myself applied for a 2-year fellowship, and Laura Ballotta visited during the year several months, and she will come back next year and stay as a fellow herself at FRIAS for several months. And the fourth co-author is Rachid Zaindin. He is a postdoc who stayed 1 year at FRIAS and another year at the Strasbourg Institute for Advanced Studies, which is very close. But before I go into the topic here, let me announce our book. So this was a 10-year project. It's finished now and will come out this month. So it's about mathematical finance on the level of semi-martingales, and we hope that it bridges a gap which I see, at least as far as models with chumps are concerned, and we hope that it will open the road for many people to use models which use chumps.
Now, does anybody die? Is there a murder?
No murder in the book so far, maybe in the second edition. So is there a murder in your book?
Yes.
There is. There is. Okay. Now, Venice, of course, is more romantic than mathematical finance. But, I mean, you have here 400 pages of stochastic analysis, and the following 350 pages are on mathematical models in finance. And we hope that it is the right level to help people to enter the field as soon as you want to study more sophisticated models. It is online. You can order it already if you are interested. Christmas is not so far away. Sorry? Yeah. Okay. So it's together with Jan Carlsen, which you might know him from he's at Kiel University, and he studied with me and got his PhD with me. Now, let me come to the topic of this talk, variable annuities. Why are we going into insurance mathematics? Now, insurance currently, or life insurance, is in trouble, at least in Euro country, because we have this low interest rate environment, and this is a big problem for life insurance. No, life insurance is actually not the right word. We should here talk about endowment policies. It's not about life and death. This is in addition, but basically it's about pensions, and that's why we wanted to contribute to this topic. I mean, variable annuities are not new at all. Nevertheless, they are, as far as I believe, the right product to help in the current situation, because I do not think that you can recommend to anybody currently to sign a traditional life insurance contract. The guaranteed rate in Germany is below 1%. It's 0.9. It has been for a long period 3.5%. For a short period, went even up to 4%. But now it is below 1%. And given some inflation, the ECB wants to raise inflation, but we have some inflation, and the inflation covers only the cost of living. It does not include rent. It does not include the house prices, etc. So why should you sign a 30-year contract with a guarantee of less than 1%? And this is a product which helps to offer a reasonable contract. So there's a large variety of designs in the market, and we will study one particular design. If you're interested in this large variety, there's a nice survey paper by Baccinello and co-authors where they classify the various designs, and there's quite some literature about the valuation and the risk management of these contracts. All these which are listed here are diffusion type models to value variable annuities. We go beyond that. But what we want in particular emphasize is that there are options embedded. And this is a conference on options, and these are notoriously neglected in the literature, but as you will see at the end, they are really important for the value of the contract. By the way, I mentioned that these are diffusion models. Laura was the first one to use Lévy processes in a 2005 papers, of course in a much simpler context as we do here, but also Lévy processes are not totally new in this context. The design which we study in the paper, which is accepted in quantitative finance, is the following. You might make it to maturity, and then you get the better of a guaranteed rate, given here in the continuously compounding way, e power delta t, I is the face value, or you get the value of a reference portfolio, typically an index, DAX in Germany, CAC in France, etc. But there are options. Typically, you have a surrender option. At certain time points, let's say at the end of each year, you are allowed to terminate the contract. And then the payoff typically is the value of this underlying portfolio at that time when you surrender, but penalized. You do not get the full value. There is a penalty function P, which increases as time goes on. And then there's a probability that you die. And then your family might want to have something. And in this design here, it's the same as you get at maturity. It's the better one of the guaranteed rate or the reference portfolio. We talk here about monitoring time points, maybe every quarter. If the policyholder died in the past 3 months, then the payment is made at the end of the quarter, or any other time scale can be considered here. But let me briefly mention there are alternative designs as well. One is a ratchet guarantee. That means you have certain monitoring time points where you consider the value of the reference portfolio and you get the maximum. And of course, this is a sort of look-back option, and it's a very expensive contract by its very nature. Or you can even combine this with a guaranteed rate and get the maximum of this ratchet design and a guaranteed rate. And what we study currently in a second paper is this compounding of a reference portfolio. That means you consider typically annually the performance of your reference portfolio, and this is compounded, and it is capped and floored. I mean capped because the insurance company should have some money to give you a guarantee rate, and the guarantee comes from the floor which you build in, and then you have a certain participation rate of this portfolio. So this is a very attractive design, and it will be in a second paper, which is in a very advanced stage already, so we have to program it and show some numerical results as well. But what we study now is this design, which has three outcomes. You need a dynamic for the financial market, because you consider this reference portfolio. You need a dynamic for the policyholder behavior. The insurance companies, of course, have some statistics showing that there's quite some percentage of people who surrender during the lifetime of the contract. And, of course, there is this knowledge about mortality in the insurance companies, which has to be modeled as well. So,
why is it an annuity if there is a single payment?
well, this is one design which is not so popular in Germany, but it is well known in the Anglo-Saxon world, that you start with an initial payment, the price. That's what we want to get. What is the right price for this face value, I? And this means that you have some money and you give the responsibility for what you get, what you have in 30 years to the insurance company. That's one possibility. But of course, you have also these contracts where you have an annual premium, etc. But this exists quite well. So the first dynamics which we have to consider is, how does the financial market behave? And you are not surprised that I use drivers, the Lévy processes, as drivers. And the important fact is that we use here a hybrid model, because if you have a long time horizon, and we are talking here about 20, 30 years of lifetime of this contract, then the dependence, which you certainly are aware of, between interest rates and the stock market has to be taken into account. And how do we do this? If you would be in a Gaussian world, of course, you would consider correlation matrices between the drivers of these two dynamics, but this is more complicated in Lévy processes. So we do it in a relatively simple and efficient way here. We consider Lévy-Hischaro-Morton model, the instantaneous forward rate, which I developed 15 years ago. So if you look at the dynamics of the bond prices, this is the equation here, and you have to make sure that you have an arbitrage-free model, so the drift has to be chosen accordingly. That's easy to see how you have to choose the drift. Actually, other people wrote whole papers about this, but you can see it was in 3 lines how you have to define the drift in order to have a arbitrage-free model. And now the stock price is modeled in the usual way. Here you have the discount factor, then you have the random term, and we add now the driver of the interest rate dynamics to the dynamics of the stock price. So we have here a function beta t by which you can quantify how much influence you want to have, and you have to study, of course, that this creates, that this allows the right level of dependence at all. And the whole construction is in a paper with my students, Markus Rudmann, that has appeared in Applied Mathematical Finance last year. And we assume independence of these two drivers. This is crucial for the analysis which will follow. And of course, you can go beyond Lévy processes by using time inhomogeneous Lévy process. That means you drop stationarity, and everything then becomes, the whole characteristic becomes dependent on time, but analytically this is still easy to handle. The second dynamic, and this is very important here because the emphasis is on surrender. This has been neglected in the literature so far, and surrender is a substantial risk for the insurance industry because they have to put reserves aside. They do not know how many people will terminate the contract during the lifetime, but this is a loss of liquidity, of course. And there are two major reasons why people terminate their contract. The first is a rational one, namely, let's look at this process which we define here. We look here at the return in case you surrender at time small t. This is the return of the stock market of the underlying portfolio. This is a penalty term, so logarithm between 0 and 1 is negative, so we subtract something. Where is he? The entropy function has to be taken negative to get a positive value. And this is when you invest, this is the return when you invest in the interest rate market after surrender. So this is what you get in case of surrender, and you take the spread with respect to the guaranteed rate. This is a rational quantity which can motivate to terminate and to invest if the interest rate market is attractive and if the stock market is at an interesting point. But in addition to that, there are many personal reasons why people terminate a contract, personal reasons like divorce, like you lose your job, etc. And both go now into this surrender intensity. We have a baseline surrender intensity, that's the capital C here, which covers these personal contingencies. And then we have here a factor, a process, which covers the rational point of view when it becomes attractive for you to switch into personal investment. And then the probability of no surrender is given by this equation. And if that you surrender after TI, these are the time points where you are allowed to surrender, is given by this equation. And the probability of no surrender at all is given here. And finally, and this is not new at all, we have a mortality model, the dynamics that you die during the lifetime of the contract. You need a survival probability given via an intensity. And we start with the classical Gombrich-Markham model with two parameters. But you know that mortality is not a static thing. We get older and older, and also there are fluctuations in mortality. Therefore, people use now such a mortality improvement ratio, which is given by an OU process driven by a third independent Lévy process. And you multiply this deterministic mortality intensity by this process. So we have three possibilities now. Either you are still alive at maturity, then you have the choice between these two outcomes. You did not surrender, you did not die. Or you exercised your surrender option at time point TI while being still alive, and then you get this payout, or you died during one of these intervals which we consider, and the payout to your family is then this one. And then these three events are exclusive. We can add up. And the valuation is done in the usual way that we just discount these three payoffs and take expectation under risk-neutral probability. Let me very briefly indicate how one can handle these complicated payoffs? Now, the first thing, we assume that the mortality process is independent of the financial processes. And this allows you to take this indicator as a probability out. Then you have still a quite sophisticated expectation to compute, but this maximum can be written as, where is it? Can be written as you pull the deterministic term, this e power delta t out, and then it's 1 plus a call option. And the other term, which refers to the surrender possibility, is first written as a conditional expectation here. This is measurable with respect to capital T. And then we have an intensity here, and using this trick again, together with switching to the forward measure, which swallows the discount factor, we finally get a reasonable quantity, namely it's just this surrender intensity, and this comes from the 1, and here we have an additional call payoff multiplied with surrender. So we have two terms which have to be evaluated under the forward measure. Sorry?
Are you assuming that the market is complete?
No, we are here in a Lévy world. The market is not complete.
So which risk neutral valuation? One of them?
Yeah, you have to calibrate. You have to calibrate.
And you're assuming mortality independent of the investigator?
Yes. This is what you have in solvency. Solvency is risk neutral valuation.
There are many papers where they force dependence. There is a strong correlation between mortality and interest rate, mostly in the long run.
Oh, that's new to me, that the mortality depends on the interest rate market. My God, I live in Germany.
Think about the converse.
So we are at 0 interest rate, and you say mortality is related to that. It's a very dangerous country.
Think about the converse. There is an impact on the mortality on the interest rate, especially in the long run. I mean, it's not me. There are many papers.
Anyhow, we are oriented here towards the solvency rules, and solvency is risk neutral valuation. And of course, my co-author, Thorsten Schmidt, is working a lot currently on this PQ evaluation, where you start to value first under P, and you take the protection, the real measure, which you observe, and then you project, and you take finally the valuation under Q. Now, just a brief word about these evaluations. So since we have a piecewise constant intensity, this translates into in the exponent, this translates into a product, and so we end up with expectation of a function evaluated at a certain vector of this process, which models the spread between the outcome without the outcome if you surrender and the guaranteed rate. And this is a quantity which one can handle with Fourier-based techniques, so you end up with an integral. The second term is a bit more sophisticated because you have still this call option here, but the call option is dependent on this process at maturity, so the vector becomes just longer and the function a bit more sophisticated. So we end up with a theorem for the GMAB, the accumulation benefit, which is a nice analytic expression if you accept that you have to evaluate this integral here. Now the other terms are of a similar structure. Actually, the surrender is a bit more, it's simpler. It's just a sum, but each term here is simpler because you have just the value of the underlying portfolio. Yes. And then we have the death benefit. It looks complicated, but it is of the same structure because we have many more time points where the death event is monitored. Now, implementation, we used normal inverse Gaussian process because it has a very simple cumulant function. This is the driver of the mortality improvement ratio. These are the survival probabilities. They can be given in explicit terms. We used Monte Carlo integration. I want to show you this picture. This is the real part of this function which has to be integrated. And if you look at it, it's not so far away from a multidimensional normal. And therefore, we used important sampling to speed it up and to make it more precise, this numerical Monte Carlo integration. And here are the parameters which we used for a 10-year contract. A 10-year contract, the 3 and 4 years were considered to benchmark the algorithms. And well, we looked at a 6 months monitoring of death and an annual possibility to surrender. Now, these are the parameters of the financial market. These are the 2 parameters of the surrender model. And here are the parameters of the mortality model. So these are the results. I just want to point out that the integration routine which you might have on your computer works until dimension 3. We have to go beyond that. But even in dimension 3, you see the CPU time for this routine is already 10 times of what you have with this Monte Carlo integration with important sampling. So this is really the right strategy. Here are the values, the different components for the 10-year contract for which we got explicit values, but it's better to show you pictures. And this underlines how important it is to model surrender. The surrender option has a tremendous influence on the value of the option, of the value of the whole contract. So this is the accumulation benefit component. This is the death, and this is the surrender component. You see there are massive differences as soon as we play with the parameters. So we have to calibrate this. We have now some data which will be done in the second paper. Now, this is the dependence of this dependence parameter, dependence between stock and bond market. And finally, we have here the dependence on the guaranteed rate, 1%, 2%, 3%. Of course, this has also a significant influence on the contract value. So the paper is accepted at Quantitative Finance, and you can download it from Archive and SSRN if you're interested. I can actually already send you the copy from, it's electronically available already if you're interested. Thank you.
So to keep up with the schedule,